overall carbon intensity of the worldwide economy. And the dotted lines here represent the carbon intensity of the new energy sources that we would add. Of course, energy sources amortize and get depreciated over time, usually like 40 or 50 years. So that means essentially we have to go almost immediately, rather soberingly, to nearly zero carbon intensity energy sources in order to meet the 2-degree scenario, which is essentially what the world's leaders signed up for in Paris. And this seems like a very daunting task. So I think there are two messages here. One is that we need to develop scalable technologies for dispatchable, meaning available anytime of the month or year or day or night, sources of carbon-free energy. We need to do it quickly, and probably because of the challenge here, we're going to need some form of negative carbon emissions at some point. And that's a big, audacious task ahead of us. So in essence, what we're aiming for is something like this. This is from a recent survey paper in Science that sort of shows what are kind of the building blocks of a renewable energy infrastructure that we can anticipate trying to develop in the future, where we have essentially energy systems. What do we have now? We have basically utility infrastructure for water and power in many advanced places in the world. We have gas pipeline networks and things like that. And in a more closed system energy economy, we can anticipate that we might have a power network, shown here in light green, a hydrogen dispatch and distribution network between sources and use points for energy, a oxygenated hydrocarbons or alcohols, perhaps infrastructure, and then maybe even an ammonia infrastructure as well. So this is kind of what we anticipate that we may end up needing. And then also we may have a CO2 infrastructure that involves some aspect of sequestration if we're not successful at figuring out how to do the capture and conversion and negative emissions that we need to do some other way. So are there any precedents for this? Can we actually transform the infrastructure, and are there scalable manufacturing technologies can do this? And I think when I was a graduate student, this technology of solar energy technology was very much a figment of people's belief and imagination, but it certainly was nowhere near reality. In fact, when I was a student at MIT, there were approximately 5 megawatts worldwide production capacity of photovoltaics at the time. And today, we are at a worldwide production capacity for photovoltaics of 100 gigawatts with a cumulative install of 400 gigawatts. If you think that's now starting to get, of course, this is gigawatts peak, not electric, but nonetheless, it's starting to get to numbers that are looking to be at least only an order of magnitude away from the scale of energy use, global energy use. It's also become the world's largest optoelectronics industry. It's surpassed now in both growth rate and turnover the flat panel display industry, and it's about a third of the size of the merchant semiconductor industry. So it's become a worldwide industry. It's diverse. It has a materials supply chain, equipment, distribution, project finance, a lot of things, a mature industry. Currently, the cell technology uses silicon. The predominant cell technology, 90% of the technology uses silicon photovoltaics, record efficiencies in the mid-20s %. Commercial efficiencies are in the range of more like 17 to maybe 20%, maybe pushing at 21%. But the real story is the cost reduction. And if you haven't looked at today at the cost of photovoltaics, your information is out of date. In fact, the costs have dropped in the last year and a half by a factor of 2. Remarkably. So it hasn't really, you might not have been paying attention, but that's been going on. And I was recently at a meeting in China where 5 of the top 12 photovoltaics company CEOs were assembled and were all asked where they thought the floor was on photovoltaic price of electricity or module cost. None of them saw a floor. Actually, they anticipated electricity could potentially go down to 2 cents a kilowatt hour or so in many locations in the world, and the module price could drop to maybe 15 or 20 cents a watt. And didn't really see any reason why it couldn't go lower. So that's that's an example of an industry that has emerged that maybe can give us some optimism that I think there are two lessons out of this. One is that we have at least one industry that has been able to generate, at least at the intermittently dispatched level, very inexpensive electrons. Both wind and solar have that characteristic nowadays. Of course, making dispatchable energy is a different question. But we've also developed a worldwide industry that can make, for less than the cost of a double pane window, an energy converter that's about 20% efficient from sunlight to electricity. And that's quite remarkable, I think. Let's see if my advancer is out of power. One of the challenges is that in the dispatchability, and that has to do with the fact that solar energy is intermittent. It's predictably intermittent, of course, on a diurnal cycle. It's somewhat countercyclical in its availability with wind power generation. Wind tends to be, in many locations, more available at night. But the sum of the solar and wind generation doesn't perfectly match the demand cycle in most places. And so we're going to have some form of energy storage and dispatch in order to make energy available on demand. So, of course, it's not only daily variable, there's also seasonal variability that we need to think about. In November, last November, I was in Gothenburg, Sweden, and there the solar flux at noon is an order of magnitude smaller than it is, for example, in July. So there's a seasonal variability in northern climates like that. They actually used hydropower from Norway to make up for essentially to ballast renewables in the Scandinavian countries. So what are some options that we might have for dispatchable solar energy at scale? And I see basically two options. One is that we have to make PV more pervasive and even lower cost than it is today. So it's a kind of an amazing story that we've gotten to the low cost and pervasive scalable technology that we have. But it has to go even lower in cost, and it has to go lower in cost so that we can afford the cost of the storage. Because to make a dispatchable energy system, we need both the primary generation source, which is intermittent, and we need storage. And I think also, while the silicon technology has been able to be scaled, it's mature in its technology, and it's reaching very much to the efficiency limits, and we're not going to be able to achieve significantly higher efficiencies. But we could, in fact, lower the overall cost of photovoltaics very considerably simply by increasing the efficiency if we could manufacture at the same cost something with greater efficiency, because even though a module is a very small fraction of the total system cost of a photovoltaic system, raising the efficiency lowers the cost of the entire system. So it's much better on a marginal basis to work on raising the efficiency than lowering the cost of the panel to lower the cost of electricity. And the second is to develop methods for synthesis of chemical fuels from sunlight. Essentially, chemical fuels that we use in transportation essentially represent a form of almost arbitrary storage. And if we can make that dispatchable, that could be a very powerful part of our economy. So where do we stand with photovoltaics? By the way, I'm wondering if there's any other pointer other than my pointer available to know whether there's a pointer here. Okay, well, I will persevere without. Okay, or actually, I can probably get another one here.
All right.
Okay, Tito is prepared. Oh, that's not too bad. Okay, good. So if we look at this is a nice inner comparison of photovoltaics technologies. This is from a paper from Albert Coleman's group in Science from a couple of years ago that basically plots the normalized photocurrent density relative to the theoretical limit, the Shockley-Queisser limit, and the open circuit voltage times the fill factor, which is some measure of the product of these is a measure of the power generation. And so one wants to be in the upper right portion of this plot. And this is essentially a compendium of all of the technologies for photovoltaics that have ever essentially emerged beyond the laboratory scale. And you can see here that several technologies here failed to reach above 50% of either the Shockley Queisser limit, either on the basis of voltage or current. And a number are in the range of 50 to 75%, and some have reached either 75% and above. And the ones that have reached above 75%, particularly on the voltage, are ones that are essentially, we know as optoelectronic materials. Gallium arsenide and gallium indium phosphide, these are the basis of our telecommunications. They're used for lasers and LEDs. In fact, the LED that I'm pointing at the screen with is a frequency doubled LED using a 3-5 pump diode. So then basically, if we have our opportunity to use these almost ideal materials for photovoltaics, these are the ones we would use. You notice crystalline silicon here is just barely into the threshold of high efficiency with respect to voltage, but it's been nearly optimized in terms of photocurrent density. Okay, so what are the opportunities here for using these very high radiative efficiency materials? And by the way, notice that there are some contenders here that are rising. In fact, the hybrid organic inorganic perovskites have shown dramatic increases in both voltage and current, although stability is still a major challenge for those materials. So if we think about the initial models that were developed by Shockley and Queisser, who gave us sort of a foundational framework for understanding the limiting efficiency of photovoltaics, they imagined photovoltaics being essentially dictated by a flux balance, a radiative flux balance between absorption of photons and emission of photons in a material. And it was in this radiative limit where all of the recombination processes for the excited carriers created by absorption are returned by radiative emission that we reach the maximum intensity limit. And so one of the lessons of this radiative flux balance is that actually in order to have optimal absorption, we also have to have emission of sunlight. So in the case where we get rid of all of the non-radiative recombination centers, defects and impurities in materials, and we're left only with radiative emission, then we have, in a direct bandgap, high radiative efficiency material, a material that is an ideal optoelectronic material. So in fact, the ideal solar cell material would be the ideal LED or laser material. So a high efficiency solar cell should literally glow with luminescence. For most solar cell band gaps, you'd have to be the guy in Star Trek that sees in the infrared to see the luminescence. But in some cases, when the band gap is wide enough, you can see it in the visible regime. So we tend to think about the excitations in semiconductors as consisting of exciting carriers from filled states in the valence band to empty states in the conduction band. That's an energetic picture that sort of complements this flux balance. But if we consider jointly the flux balance plus the energy picture, we can think in terms, thermodynamic terms, in terms of a Helmholtz free energy for photons and the interchange between photons and the excited carrier population in the semiconductor. And then we can identify this energy change from valence band to conduction band as being an internal energy and enthalpy. But the free energy, which is the factor that dictates the open circuit voltage, is also limited by entropic processes. And it's these important entropic processes that produce the fundamental limits. They're the things that give rise to the difference between the open circuit voltage and the band gap. And so naively, you would expect from this picture the band gap would be equal to the open circuit voltage. It's not. It's usually, in fact, in the best materials, there is a very fundamental process that's very difficult to get around. It has to do with the fact that photons coming from the sun are highly collimated. They're almost as collimated as the photons coming out of my laser pointer pointing at the screen. It's a very narrow angular divergence, and in a mode density picture that corresponds to a very small entropy of photons. A very small number of optical modes are being populated. When I have the opposite process that is returning the light from the solar cell back out of the cell, radiative emission, that's an isotropic distribution for spontaneous emission. So that corresponds to an entropy increase due to the number of optical modes that are populated. And that energy associated, the KT associated with this entropy, TS associated with the entropy process, it gives rise to an energy shift of about 300 millivolts. And so for the best solar cells, you'll always see typically, unless you do something to restrict the angular emission of photons radiated back from the solar cell to about 300 millivolts. we actually have done experiments where we've done this using angularly selected filters, and you can see an increase in the open circuit voltage when you restrict the angle of emission. But it's not a very practical thing to do. However, these are the terms that we can do something about, and these are the things that dictate the difference between efficiency, medium and high efficiency photovoltaics. So in a sort of more pictorial representation, we can view the flux balance that generates the open circuit voltage, that is essentially the chemical potential difference between the electrons and holes. And that flux balance can be thought of as, in this sort of fluid analogy, as sunlight, which is photogeneration, which is like fluid filling up a bucket with some water level that generates a pressure that's analogous to the voltage. And these recombination processes, both radiative and non-radiative, give rise to loss processes that look like leaks in the bucket. And so, in fact, if I stem all of these leaks except for the necessary one, which is radiative emission, I reach the maximum voltage. And that insight is the thing that drove us to think about using very high radiative efficiency semiconductors. So, roughly speaking, you can divide conceptually the thinking about photovoltaics into what I call the old physics, where we think about maximizing the efficiency of the solar cell by maximizing the light absorption, creating electron-hole pairs, creating internal electric fields that do charge separation and collection, from the new physics, which concentrates on the fact that in materials with very high radiative efficiency, I have within the material photon recycling. Absorbed photons internally re-radiate photons that are then reabsorbed, which are then re-emitted and reabsorbed, and so on, up to 100 times. Because with materials like gallium arsenide, we can have materials where the internal radiative efficiency, the internal quantum efficiency for radiative emission, can be greater than 99%. Can be greater than 99.9%. Can be almost 99.99%. And so that means there's this internal re-radiation, and you can see now, if you're a semiconductor physicist, that corresponds to now an enhanced carrier population, an enhanced splitting of the quasi-Fermi levels or the electron hole chemical potentials, and therefore a higher voltage. And it's that insight that led us to develop thin-film gallium arsenide solar cells, particularly if you have them on a mirror-like reflecting substrate with a reflectivity of 1. The light gets trapped very efficiently. And so what we did was to develop a process where instead of making solar cells in a direct bandgap semiconductor on a bulk substrate where photons can then be lost in the index matched substrate, we put them on a reflecting back substrate. And we made this in a process where thin films of single crystal material literally peeled off the wafer on which they're grown. So this is a lightweight, flexible, thin film solar cell. It's a 27% efficient solar cell. So this is made with gallium arsenide. You can see it's very lightweight. I'll pass it around here. So these are single crystal thin films. This is what they look like when they're tiled in a module type process. And so this type of cell now holds the one sun world record for photovoltaic conversion efficiency of 28.9% for a single junction solar cell. Actually, this number is out of date. I should have corrected that. That's now 32.2% actually for the two junction cell. And earlier this year, Alta Devices, which is the company that we founded to commercialize this technology, set a world record for the first greater than 25% efficient module. So it's really, if you look at the current density, the current densities are comparable to the current densities from previous solar cells, but the world record was achieved by increasing the voltage through the photon recycling and extraction processes that I mentioned. So this is just to tell you a little bit about the story of this company. It's now about 10 years old. I started this company together with Professor Eli Yablunovich of University of California, Berkeley. It was funded by venture capitalists, Kleiner Perkins on Sand Hill Road in Palo Alto. We developed this during the time when there was lots of money going into early stage solar companies. We set early records. We developed new tools for growth. This is the CEO standing in front of the machines that grow materials by chemical vapor deposition. This shows solar cells on the wings of electric-powered airplanes, unmanned aerial vehicles. One of the things that happened was that in the time between when we set records and started building a pilot line, the price of silicon photovoltaics dropped sharply. And many early and disruptive thin film photovoltaics companies were driven out of business. That was not the case with Alta devices. We actually were able to sustain, we have essentially a unique production process that involves growth by epitaxial growth to make the single crystal layers. This peeling process, we peel off micron thickness layers of semiconductor like a Post-it note being peeled off a pad of Post-its. If anybody still uses Post-its nowadays, I don't know if anybody does, but at least you've probably heard of it. And then those single crystal wafers are recycled, and that actually dramatically reduces the cost of the manufacturing process. Then front contacts are formed, and they're separated to make the cells that I'm passing around to you now. And so in the process of being able to make these record efficiency, lightweight photovoltaics, in addition to the mainstream solar market, which is currently hard to access with an early stage technology, we've been able to go into many other markets: automotive, Internet of Things sensors that are powered wirelessly by ambient room light, UAVs, remote power, mobile devices, charging, and so forth, that all are growing exponentially and actually are all big businesses that are currently the market opportunity exceeds the production capacity. So these are two others that have grown dramatically. Building integrated photovoltaics, this is a solar tile that's been created, and automotive. So this is something we didn't imagine when the company was started, which is that automotive companies are taking very seriously the idea of embedding something like 2 to 4 square meters of high efficiency photovoltaics directly onto vehicles so that you can have essentially a plugless rechargeable electric vehicle. And in fact, during a diurnal cycle, you can generate 8 to 10 kilowatt hours of electricity with 5 to 6 hours of sunlight on 2.5 square meters of the Alta devices photovoltaics. In fact, this is a concept car that has been developed by Alta, and it's been exhibited at world auto shows. And the electricity generated in this diurnal cycle corresponds to a range extension for the electric vehicle of 80 kilometers. And guess what? That's less than the commuting distance that most people drive every day. So if you park in the sun, you could think about having a wirelessly recharged vehicle. In fact, that's led to joint ventures with Toyota and Volkswagen and Audi to develop this. And you can imagine that could take off to be an industry that would be even comparable to the size of today's photovoltaic industry if it were widespread. Let me just say a little bit. We're also interested in impacting the mainstream solar power generation market, and many people think that the next transition for solar energy will be to go to some sort of tandem photovoltaic structure. For example, a perovskite cell laminated on a silicon module using chalcogenide semiconductors. Tandem, I'll talk about this in a minute, a so-called luminescent solar concentrator. Or the 3,5 materials that I've talked about could be made in tandem with silicon to achieve the highest efficiency. In fact, they've set efficiency records, but in flat plate form, they're probably going to be too expensive. So we were interested in the question, how could we actually use this now more expensive 3,5 material to create a cost-effective tandem? And we think the answer lies with something called a luminescent solar concentrator. And a luminescent solar concentrator is a planar waveguide, a planar optical waveguide that's optically transparent to sunlight, that has embedded luminophores. In other words, materials that absorb. Conventionally, these were photochromic organic dyes, organic molecules. We now use inorganic quantum dots. They have very high radiative efficiency, and the sort of physics that I told you about of photon trapping and recycling is also operative in these luminescent solar concentrators, just like it is in the high efficiency direct bandgap solar cells. And in this case, we use also light trapping mirrors to trap luminescence radiation. And so then light is effectively absorbed in the vicinity of a small solar cell and captured and concentrated onto a small solar cell from a larger capture zone. And that geometric gain relating, which is the absorption area over the collecting solar cell area, defines the concentration factor in the limit that all those photons are collected. So this structure is now designed to have a top cell of indium gallium phosphide on top of a silicon cell. So it's essentially something you could put on top of a conventional mass manufactured silicon module to increase its efficiency. So these are the spectral characteristics. The quantum dots are cadmium selenide quantum dots. You can also use 3,5 quantum dots that have a Stokes shift between their absorption and emission bands. That's actually fundamentally important for the concentration, thermodynamics of the concentration. This is overlapped, the emission of the quantum dots, with the absorption spectrum of these indium gallium phosphide solar cells. And that absorbs and converts the blue portion of the spectrum with higher conversion efficiency than the underlying silicon. The silicon, then the module is transparent at long wavelengths to the top layer, and then that portion of the spectrum is converted by the conventional silicon module. And so if one could obtain concentration factors greater than 40 by using quantum dots that have high radiative efficiency, this theme is coming back again of photon recycling and radiative efficiency, one could achieve that this number is actually, this concentration factor is contingent on high radiative efficiency, and quantum dots must also have a Stokes ratio, the ratio of their absorption to emission at the emission wavelength, greater than 50, mirrors that trap the light efficiently with efficiency greater than 99%. In that case, we could achieve these concentration factors, and that would be able to generate a module in this flat plate form would have efficiency greater than 30%. And by the way, this is compared to many of the other materials that are being considered for such tandems. These are all known materials. They're known to be stable. The quantum dots, by the way, are now commercially available. You can buy a TV from Samsung that's called a QLED TV. QLED means quantum dot LED, so the light is pumped from a back illuminator that photopumps luminescent quantum dots to generate color. So they're generated already at the meter scale, module scale level, and so are the solar cells. So this is what the luminescent solar concentrator looked like. Remember I said that you could literally see the glow. For the luminescence of the cadmium selenide quantum dots, they glow in the orange, and so you see orange light emanating from the edge of the concentrator. You don't see it coming out the top. That's because we have these light trapping mirrors on the top that are enabling relatively high concentration factors. The physics of luminescent solar concentration involves a trade-off between photon energy and entropy, once again. So knowing something about the entropy of light turns out to be quite interesting and leveraging for thinking about photonic design. And in particular, in this paper that my colleague Eli Yablunovich developed a long time ago now, almost 40 years ago, he showed that the concentration factor is fundamentally related to the downshift of the photon energy. So essentially, you enable a reduction in entropy along with a reduction in photon energy. And in fact, you can express this as a ratio, as a proportionality between the concentration factor and the downshifting or Stokes shift of the downshifting energy. And in principle, if you could do this perfectly and trap the photons perfectly, you could actually generate concentrations that exceed the ray optical concentration limit of sunlight. In other words, you could go to higher concentration factors than you could achieve with lenses and mirrors. That regime is inaccessible, and in fact, up to recently, the best luminescent solar concentrators had concentration factors of only about 10, primarily because they're limited by the radiative efficiency and the photon trapping in the planar waveguide that limits the concentration. By use of core shell quantum dots, these are quantum dots made by my colleague Paul Alvisados in Berkeley, they have radiative efficiency that is actually very difficult to distinguish from unity. In fact, we've been able to recently show that the quantum efficiency using more sensitive measurement techniques than this, which is a conventional PL quantum yield measurement, using something called photothermal deflection spectroscopy that measures the non-radiative component, is that the luminescence quantum yield is 99.98% for these quantum dots, which is high enough to achieve the concentration factors. And so we also use very efficient indium gallium phosphide solar cells that are made at the scale of about 300 to 400 microns in size. And if we had, for example, luminescent concentrators with maybe 70 to 80% quantum yield, then the ratio between the concentration factor for light that's achievable and the geometric gain, that's the ratio of the sunlight absorption area of the luminophores to the cell collection area, would saturate. That means that you could keep increasing the sunlight collection area and you wouldn't get higher concentration because light essentially is being lost due to non-radiative recombination. If you had a very efficient photoluminescence and total internal reflection process, you could get approximate linearity of the gain concentration factor. In fact, if you could make these factors go to unity, you could make the concentration factor equal the gain. If you could, in fact, recycle photons that were emitted from the solar cells, you could even potentially go to concentration factors that exceed the gain. So historically, most LSCs were down in this regime. And so this shows a measurement of an LSC that we created using the technology that I described with an open mirror. In other words, here's the solar cell, luminophores, and so forth. And when we don't have a top mirror on top and light is escaping out the escape cone, most light is trapped due to total internal reflection, but some light escapes through the optically geometric escape cone. Then the LSC concentration saturates here about a factor of 3 or 4. On the other hand, if we put this light trapping mirror on top, we can see that there's a linear relationship between the geometric gain. It's about 0.5 in this case for this mirror and in quantum dot combination. So far, by using mirrors that have now light trapping efficiency in the band where luminescence emission is high, of greater than 99%, and less than about 5% parasitic reflection out of band, we've been able to achieve almost 40x concentration. So this is about 4 times higher than the, and it's in the range that's useful to now concentrate sunlight onto these small, relatively expensive. So roughly speaking, you could afford to use solar cells that are about 40 times more expensive than you could use them in flat plate form. So we're optimistic that we can use 3-5 solar cells to make a luminescent solar concentrator module that operates at flat plate with diffuse sunlight. Okay, I want to shift gears a little bit and I guess very quickly tell you about some work on fuels from sunlight. This is work that's being conducted by the Joint Center for Artificial Photosynthesis. It brings together many disciplines, which include the light harvesting, charge transport and recombination, the catalytic processes for reduction and oxidation of reactants to fuel products on the surfaces of electrochemical device structures. So essentially what we're doing in this case is designing prototypical photoelectrochemical devices where the photovoltage is generated not by an external battery, but by an internal photoelectrode, very much like the photovoltaics I was just showing you. But they're driving reduction and oxidation processes for example, water oxidation at the anode and water splitting or CO2 reduction at the cathode. And for those who are unfamiliar with this process, in some ways, this essentially mimics the photoelectrode operation of our most famous natural process of photosynthesis, which has 2 light harvesting centers at 680 and 700 nanometers that produce enough potential energy to generate protons and oxidized water. And the protons are used now in a dark reaction center to create NADPH, which are the building blocks for the sugars and carbohydrates that sustain the biological viability of the plant. So in artificial photosynthesis, we're going to use an inorganic photoelectrode and inorganic heterogeneous oxygen evolution catalysts and hydrogen evolution catalysts now to overcome the thermodynamic potential and the kinetic overpotentials for the water oxidation and water reduction processes. And so then to do this, we're going to use a tandem photoelectrode, very much like nature does, which uses 2 light absorption processes at different wavelengths. That allows us to build voltage and current with enough efficiency to do this in a relatively efficient manner. So the reactions we're driving are hydrogen evolution, oxygen evolution at the anode, and in the case where we have CO2 in the electrolyte as well, we can drive a variety of CO2 reduction reactions. So just to think about how this process works, we have this tandem photoelectrode that's creating a potential difference between the cathode and the anode. At the cathode and the anode, we have a current that flows, which is given by this exponential kinetic expression with an exchange current density, and the goal of developing an efficient catalyst is to be able to reduce the overpotential at a constant current density that corresponds to the solar photocurrent density. In order to operate and maximize the device efficiency, the principle of design is a little bit different from a photovoltaic. We simply want to overcome the thermodynamic potentials and the kinetic constraints to current flow at photocurrent densities, but then not waste extra potential because that is just dissipated as heat, because the current density then is the key quantity, as long as we have enough potential, to drive the water oxidation and cathode reduction reactions. So the overall efficiency then is the current density times the Faraday efficiency and the energy over the incident solar flux. So this work is being done by, as I mentioned, the Joint Center for Artificial Photosynthesis, which is a large consortium program. It's an integrated partnership led by Caltech that involves Berkeley Labs, Stanford Linear Accelerator Lab, and UC Irvine in San Diego. There are two purpose-built laboratories, one on the Caltech campus and one at Lawrence Berkeley Labs, that are designed specifically for photoelectrochemistry, solar fuels, and renewable fuel synthesis. We have more than 100 researchers and 32 PIs, so it's a relatively large and diverse program. The program is looking at materials discovery of photoelectrode materials, materials as well as catalysts, and discovering them using combinatorial synthesis by high throughput experimentation. Material synthesis for membrane separators used to safely separate the fuel products. We use in situ and operando measurements to study the properties of catalysts in their operating environments. We use theory to map the potential and kinetic landscape for different reactions, and benchmark the relative performance of different catalysts under similar conditions. And then finally build integrated prototypes that operate at the centimeter scale level, 100 square centimeter scale or so, to produce device prototypes for solar fuel generation. So I'm going to just, in the interest of time, just tell you a few elements of this and mention that, so for example, the power of high throughput discovery. So combinatorial synthesis, and in fact, I know there's about 5 minutes or so, yeah, so there's about a significant activity here in computer science at Cornell studying this process. To use combinatorial synthesis and combinatorial theory together to screen for the properties, in this case, of ternary metal oxides, which form photoanodes, materials that absorb sunlight and act as a anode for water oxidation. So they need to both have a dual function of absorbing sunlight with a band gap in the range ideally less than 2 eV, be stable in water, and also be catalytically active. So starting from thousands of candidate materials, we can develop a so-called funnel that identifies and narrows down using first principles theory. This is the materials project at Lawrence Berkeley Labs to identify promising candidates. And this is then combined with combinatorial synthesis done using inkjet printing of something that looks like a sort of drug discovery plate. And this has several thousand candidate multi-component alloys, ternary and quaternary metal oxides that are printed on a plate, and a scanning photoelectrochemical cell that quickly and rapidly makes an electrochemical CV scan to test the current voltage characteristics of each structure, as well as determine its optical absorption. So this is used to screen the photoelectrochemical performance. And so I don't have time to tell you about all of the activities in JCAP, but I want to just mention that the work done in the first 5 years of JCAP, which was focused largely on water splitting, photoelectrochemical water splitting to form hydrogen, culminated in the formation of stable oxide protected photoanode prototypes where a transparent, chemically impervious, but nonetheless conductive titanium dioxide coating served as a barrier to prevent corrosion of the underlying photoelectrode and as a support for the water oxidation catalyst. We also developed photocathode prototypes and a broad portfolio of devices that operated at about 10% efficiency. More recently, we've been able to demonstrate water splitting efficiencies as high as 19.3%. So this is actually now starting to get up to solar to hydrogen efficiencies that are comparable to the solar to electric generation efficiencies that are now routinely available. And so in the last about 2.5 years, there's been a rapid increase in, this is of course a champion device. In a minute I'll show you how it works. It uses a tandem photoelectrode and in this case a precious metal rather than abundant catalyst. But this relatively low loading of a rhodium catalyst has the interesting feature that these rhodium nanoparticles with size about 10 nanometers form a structure that is highly catalytically active and produces low overpotentials at solar photocurrent densities, but is essentially optically transparent. In fact, there's ultraviolet absorption, interband absorption in the rhodium in the short wavelength part of the spectrum. But if we compare the absorbance, this is indirectly inferred from reflectance, is comparable to that of the tandem structure with bare titanium dioxide. So it's essentially invisible to the incident sunlight. And the other feature that increased the efficiency was a sort of serendipitous factor in which the energy band alignment of the protective titanium dioxide was aligned with the conduction band of the widest band gap semiconductor and with the ruthenium catalyst supported on the surface. So the losses due to energy losses in the transport from the photoelectrode to the catalyst would minimize. So the efficiency of 19.3% at pH 0, 18.5 at pH 7, and with a membrane which reduces the resistance of which reduces the efficiency a little shy of 15%. So I'm just going to mention that at the moment JCAP is involved in and has shifted its direction towards this challenging problem of selective CO2 reduction. In other words, taking concentrated or dilute streams of CO2 and finding routes to selective and efficient conversion to reduce carbon products that go beyond carbon monoxide to transportation fuels. And I don't have time to tell you much about this. Let me just mention that we have a variety of catalytic strategies. And the catalytic strategies are designed to overcome the propensity of our best catalysts to make more than one product. So for example, one of the best catalysts for electrocatalysts for CO2 reduction is copper, which is an intermediate binding energy. Weak binding energy tends to produce few electron products. Strong binding tends to do a number of things and ultimately poisons the catalyst by saturation of the surface coverage. But by tuning the surface local environment with multiple sites generated by alloying, by generating nanoscale structures or angstrom scale structures, by binding molecular moieties to the surface, by changing the local field environment with cation electrolytes, or designing interfacial sites with controlled step densities that allows us to become selective. And another approach that we've taken is to use light as an element of selectivity. So I'll just mention here one example of a kind of a exciting result for catalytic selectivity. This is from my colleagues Jonas Peters and Teo Agapi, who showed that molecular catalyst pyridines, in this case nitrogen functionalized aeropyridinium, which initially start out as molecular catalysts in the electrolyte, condense and form a film, electrochemically deposited film on a cathode, which can now generate a dicarbon product, ethylene and ethanol and propanol fraction relative to the total reduced products of carbon of more than 80%, reduces hydrogen evolution to a few percent, and reduces the fraction of methane generated relative to C2 products by more than 2 orders of magnitude. So this is kind of an example of the kinds of things that are possible. So I'm just going to, in the interest of time, skip a I can talk for the most of the day because JCAP is a large program, and just mention that overall, with efficient photoelectrodes to generate efficient photoelectrochemical water splitting and other reduced products, together with efficient electrocatalysts, we have, I think, some cause for optimism that we can harvest this bounty of cheap solar electrons and relatively cheaply produce solar energy converters to realize essentially the building blocks for this closed cycle renewable energy landscape that we all aim to achieve. So I'll thank you very much for your attention.
Before we start the questions, I want to just point out that these lectures are organized in a lecture lunch format. So there's a lunch in 331 Upson. The room is relatively small, so make sure that you're there early. And that's, we found that over the semester, that's been a very effective way to get really detailed questions answered by the speakers. So I encourage many of you as possible to attend the lunch. All right, so we've got time for about 3 or 4 burning questions. So please go for it. Yes, way in the back.
Hi, thank you for the nice talk. I just have one question. So what limits the lifetime of the solar cells? Like, how long can we use the cell? If we...
You're asking about the usable lifetime?
Yeah, like a month or
Okay, all right. Yeah. Okay, so that turns out to be for almost any energy converter. Okay, so what is the standard by which the current energy infrastructure defines the usable lifetime? So if it's say a fossil fuel-fired power plant, it's depreciated over 40 years. A photovoltaic module is today rated to a 25 to 30-year lifetime. The commercial manufacturers, because silicon cells are so stable, they're actually talking about warranting out to 40 or maybe even 60 years, the usable lifetime of a module. So any device that you make either has to be able to last that long, or to have preventive maintenance that doesn't cost very much, such that it could be used over that length of time with reasonable efficiency. So the materials that I talked about, the 3.5 materials, have been validated to last that long. They're used, for example, in space power generation. They're used in various forms of terrestrial prototype demonstrators that show their stability. Stability is a very big issue. There's great interest in the halide perovskites right now because of the potential for low-cost, efficient processing. But the biggest challenge there that I think the community is starting to turn its attention to is stability. So that's a very important question.
Thank you.
So Harry, so you mentioned the bottomless limit, right? You said that you went to this conference in China.
Yes.
People are anticipating 2 cents per kilowatt hour. So that seems a little bit far-fetched, and it would be interesting to hear your thoughts on that. Is that realistic?
Okay. So I skipped over a slide here, maybe.
While you're at it too, Harry, can you comment on the balance of systems issue? Even if you were to drive your gallium and arsenic thing to 26–30%, that sort of is tougher to deal with, right?
Well, I would argue actually that increasing the efficiency is the best way to leverage the cost of the balance of systems.
But are you optimistic beyond 26% with these single gallium arsenide flat plate systems?
So we can immediately, with little added cost, make a dual junction cell. It's the same process. It can go to 32%, we think, relatively straightforwardly. By the way, I should mention there are other effects that I didn't get into. A typical module operates at an ambient temperature of about 50 to 60 degrees when it's out in the desert. Silicon has a degradation of about 1% relative per degree. Gallium arsenide has a 5 times less degradation of efficiency with temperature. It also operates cooler. We've actually done side-by-side tests of the 3.5 cells at NREL in the outdoor test facility next to a silicon panel, and they operate approximately 7 to 9 degrees cooler than silicon panels. It has to do with the fact that gallium arsenide absorbs less of the solar spectrum. You have this reflecting back reflector. So those two combined points mean that when you look at the annual energy production, which is what you care about if you're a utility, you can actually get something like 50% more energy out in a year from a direct band gap efficient material than you can from silicon. So that's another advantage. By the way, with regard to the question of how low can the price go, since people ask that, this is an interesting plot. In October of last year, there was a bid among commercial contractors to build a 300 megawatt solar plant in Saudi Arabia, and the low bid that was accepted was 1.8 cents per kilowatt hour. So that's a project that was built.
So in terms of dollars per watt, total installed, that would be another number. I don't know what incentives are in this system at all, if any. There might be some.
I think the biggest incentive here is that the very high solar irradiance in Saudi Arabia. So,
but still, dollars per watt is
Yeah.
dollars per peak watt number.
Yeah.
So
Right.
For yours, the best.
for the system,
Yeah, for the system. Yeah.
so I think, yeah, that's an interesting question. So I think the balance of systems would actually be, which dominates at the moment, is going to be proportionately lower based on the efficiency. But I think in the range of maybe 60 to 80 cents a watt is a reasonable concept. Yeah.
That would be great if they could
Yeah.
get to that.
Yeah.
Thank you.
Question,
Yeah.
Are there other questions? Yes. Plus.
What are the prospects for electrochemically making multi-carbon products from CO2?
Yeah, so as I mentioned, that in fact is a major focus of JCAP for time limitations. I didn't get a chance to tell you about that. Let me tell you where the community is right now. We have electrocatalytic configurations for purely dark electrochemical components that can generate dicarbon products with about 70 to 80% Faraday efficiency. The energy efficiencies are still not high enough to be commercially interesting. So there's work going on all over the world now on this. I think the record now is held by Ted Sargent in the University of Toronto. So that's quite interesting. And actually the insights are that even in aqueous electrolytes or water vapors, which are required to get to very high current densities, you actually build something that looks more like a fuel cell, where the ultimate mass transfer is limited by vapor transport rather than diffusion and a bulk liquid electrolyte. And you can operate these things at hundreds of milliamps per square centimeter. You're not quite up to 10 amps per square centimeter like in a fuel cell, but it's getting there. And so it's starting to look pretty interesting, actually. Oh, okay. Wow, C8. Wow, now you're asking hard questions. We thought we were pretty happy with ourselves for making dicarbon products. I think realistically it's going to be hard to, if you think about the number of electrons required to go to reduce, that may be out of range for a purely electrochemical or photoelectrochemical process. But some combination where you're using the early stages, using a low capital intensity, low temperature, low pressure electrochemical or photochemical system together with a thermochemical conversion downstream might be an interesting kind of scheme to use.
Okay, so one more.
Thank you for the talk. So I was from engineering. So my question is on CO2 reduction. So you mentioned there's electrophotolysis and photosynthesis.
Yeah.
So which one do you think has a more future for CRI?
Wow. Okay. Future for scale up.
Yeah.
I would say, to be perfectly blunt and honest, this is a very exciting time for the students to get into this field because I think we're still in the early stage of research area. I don't want to delude anybody to believe we're actually on the verge of building systems here. We have a long way to go, particularly in energy efficiency and so forth. You can have a sort of a religious discussion about whether electrochemical or photoelectrochemical or photocatalytic is and people will argue that the declining cost of electricity alone says you do everything in the dark. I actually think there's a lesson, which is that by making solar panels inexpensively, you've shown a pathway to $50 square meter basis very inexpensively. So I think the jury is out with respect to, and it's the next generation of students that will, and their advances together with their advisors and in their future careers that will end up determining the answer to your question, I think.
Yes, go ahead.
Yeah, where do you see the future of like TNT to be heterostructured
Ah, okay.
solar cells.
Layered materials, yeah.
To-
I didn't get a chance to talk about that. We actually have an active interest in that, and we're looking at ways that we can use 2D materials. We've been able to achieve relatively high quantum efficiencies, more than 60 or 70% in less than 10 nanometer layers of 2D materials, over 90% absorption. Right now, the challenge is to create high voltages by having alignment of the electron and hole selective contacts with the absorber layers, and then to figure out how you could develop a sort of bucket chemistry way. We can't grow by CVD or MBE. We have to figure out a way to paint things onto surfaces that, which in principle I think you could do using chemical exfoliation and liquid coating processes. But I think there's some very interesting potential there.
Is that currently scalable, like through chemical exfoliation?
It depends what you're trying to do. I mean, there are already, if you, for those of you who work in the laboratory with ultra-high vacuum systems, the anti-galling grease that you use to lubricate the bolts on your high vacuum systems are actually, the grease, the lubricant is molybdenum disulfide. So there's a commercial product you can already buy, not at square kilometer levels, but nonetheless there.
All right, thank you.